Okay, so you've already learned about horizontal launch and symmetrical angled launch, so this is asymmetrical. So instead of doing like notes that you do at home, I figured I'd do this because I figure you'll have more questions. So, all right, so for this one, it means that you start from a point and you end either at a lower point or a higher point. So it can look like this, or it can look like that, okay, where the distance from where you end to where you start is still your delta dy. The distance from where you start to where you end in the x is still delta dx, okay? And you typically will have a velocity vector, we call it v naught. So your v naught in the x direction is always v naught cosine theta, and it's the same in the x for up and down because it's going a constant velocity in the x direction. Your v naught in the y will be v naught sine theta, but your v naught or your v final in the y, this will vary by situation because it depends if you're landing higher or lower than where you started, then it'll not be the exact same, and it might not even be negative depending on where it lands. I mean, it could land like that, or you could even have a situation where you have something that starts and runs into a wall over here and it doesn't even go down. It just goes and hits the wall. So it might not even be negative. It just depends on the situation. Yes, sir?
Why do you multiply the v naught by cosine theta?
Because it's at an angle theta.
So why does the angle change the initial velocity?
What do you mean? Why does it change for the initial velocity? It doesn't change.
Why does the v initial change when the angle is different?
Because it's at an angle. It's not straight up or it's not straight side. Like it's not horizontally launched.
It has like two things that you can.
Because at that point it'll have a y and an x component. Your vy will just be straight up, where your v naught x will be straight to the side. So same thing here. You have a v naught in the y that goes straight up, and you'd have a v naught in the x that goes straight side. So you have to use trig to solve for your x and y components, and you have to keep them separate for your math because they don't influence each other at all. The only thing that's the same is the time. Nothing else is the same. Well, and I guess the v naught, but not the v naught in the x or the v naught in the y. That's why you have to use a sine or a cosine. Okay, your a in the x direction is always 0. Your a in the y, you may as well call g, and you need to make sure that you remember it's negative, because a lot of things, instead of calculating these on the AP exam, will be in terms of letters. So you're going to want to use like a letter G, not -10, not -9.81, but just G. And just know that it's a negative number. Yes, sir?
So is G positive, like G itself is 9.81?
G is 9.81, yes. So as just the magnitude, but I would use a negative if you're going to use a number, and just understand that it is drawing something down towards the earth all the time. So if it's going up, it's slowing down on the way up. If it's going down, it's speeding up on the way down. So you just have to remember those particular things all the time for G. And G is always negative. If you're not talking about magnitude, it is always negative. G is different on Earth than it is on Mars or the moon, but it is always negative. Cool? Okay. All right. Your delta x, it's in the picture here, it's delta dx. Some people like to call it range. It doesn't matter. It's the same thing. Your delta dy, so depending on the situation, so if I'm talking purely about this situation right here, it's delta dy, but notice how dy is the landing spot is below the launch spot. So what sign would this particular dy have? Negative. It'd be negative because it's below, it lands below where it started. Just like in in horizontal launch, your delta y, or your delta dy, whatever you want to call it, your displacement in the y component is always negative because it's landing below where it started. Does that make sense? Okay, cool. All right, and then the time is the same to go up and down, or to hit whatever it's hitting, it's the same. Your impact velocity, again, we don't really, I don't know that you'll use this a whole lot, but your impact velocity is just the square root of the v final in the x squared plus the v final in the y squared. And your theta of your impact is not necessarily the same as your theta for launch because it's going to land in a different spot, so the angle is going to be different. So I like to use inverse tangent of Vy over Vx. So, and then people say, well, how do you find Vy? Well, usually you'll have time, you know gravity, so your V and the Y, I would just use the AT plus V naught, but these are going to have to be for the Y, right? So I would use something of this nature to find it, and your A obviously is going to be G, so it's going to be negative. So your Vy, depending on your situation and how long it's in the air and the magnitude of your V naught Y. I'm so sorry. There we go. So sorry. Okay. You guys are like waving at me and I'm seeing nothing. Sorry. Okay. Yeah, so there's impact velocity, there's the impact angle. This is the one where I use tangent personally. This is kind of I love to use tangent for that. You could use sine and cosine if you prefer, I don't care. All right, so description of the horizontal motion in graphs, it's the same as it was for the last two types of launches. So, it's constant velocity, and we typically think of it as constant positive velocity, so it's just going to be a straight line with a positive slope for the position time graph. For the velocity time graph, it's going to be a flat line with zero slope in the positive quadrant. And for acceleration, it's not accelerating because it's constant velocity, so since the slope of your v versus t is zero, the slope of your acceleration line hits at zero on the y-axis. Now, your vertical motion, it's going to depend really on where you start and where you end for the position time, but the velocity versus time is kind of easy, and the acceleration versus time is also kind of easy. It just depends on the situation. So I'm drawing these graphs for this situation. So for this situation, you see how it starts at an x value that's higher than where it lands? So if I want to keep all of that in the positive quadrant, because that's just where I like to be, in the positive, I'm going to start my height at a higher spot than where I land. I'm going to make my landing be on the zero, okay? So that means for my x versus t, I'm not going to start at the zero. I'm going to start higher, and it's going to go up to zero and then come back down, and it'll be a negative slope on the way down. So it's positive going up, zero, and then negative. So v versus t, positive, zero, negative. And then a versus t is always just negative 10, so it's going to be just a line in the negative. Okay? So the graphs are kind of the same, it's just your position is going to start in a different spot for asymmetrical. All right, so let's look at example 2. All right, so it says you have a ball of mass 0.5 kilogram, initially at rest, kicked directly towards a fence at 32 meters away, as shown above. The velocity of the ball as it leaves the kicker's foot is 20 meters per second. So this is my V initial, okay, is 20 meters per second. My 32 meters, this is my delta dx, okay, at an angle of 37 degrees, and they've told me sine 37, cosine 37, tangent 37, above the horizontal. The top of the, so this is my theta, sorry, I'm gonna label everything. The top of the fence is 2.5 meters high. The kicker's foot is in contact with the ball for a 0.05 seconds. The ball hits nothing while in flight, and air resistance is negligible. So first, I need to determine the time it takes for the ball to reach the plane of the fence. All right, so that's going to be, I have the horizontal distance to the fence. I don't know if it's actually going to hit the fence or not, so I can't really use this 2.5 meters. So I can use this, though, especially considering I know that it's 32 meters away. I know the initial. I know I know my V naught in the x direction is V naught cosine theta. So that's just going to be 20 times 0.8. So the way I think of this is I just do in my head just 0.8. So that would mean I could divide this into 5 parts. So what's 20 divided by 5? 4. And this is like 4 parts of 1. So it's 16. So that's not a 16, sorry. 16 meters per second. So that's my V naught and the x. I know that it's going a constant velocity in the x direction. So that's going to be, so my delta x, or delta dx I should say, is equal to my V naught in the x times time. So if I want the time, I just divide by V naught in the x. So my dx is 32 divided by 16, which is 2 seconds, okay? And it says the kicker's foot is in contact with the ball for 0.05 seconds. 0.05 compared to 2, that's pretty negligible. So I would say determine the time it takes for the ball to reach the fence. It is exactly 2.05 seconds, but I would probably answer this as about 2 seconds. You could say the plus 0.05 seconds, but in reality, that's not going to matter because it's not enough time for anything. But it's about 2 seconds is probably a better answer than this. You're going fast. 2 is closer. There's not going to be any difference in your math between 2 seconds and 2.05 seconds. It's too small. Does that make sense? Cool. All right, moving on. Then I want to know, will the ball hit the fence? So I know the time is about 2 seconds, okay? I know that my y value is going to depend only on time. It's not going to depend on how far it goes horizontally. But because that's all the information they gave us, we had to determine time using the horizontal portion, okay? So as far as how far will it be, well, my delta dy, okay, sorry, I'm dying. V naught in the y, t plus gt squared over 2. Okay, well, my V naught in the y. So let's look at that real quick. My V naught in the y, it's going to be V naught sine theta. So think of that as 20, and then sine theta is 0.60. So you remember how we said we divide 20 into 5 parts, so it's 4, and 0.6 is 3 parts of 1, so it's just 4 times 3, so it should be 12. And it's positive because of, look at where the vector is. My V naught in the y is going upwards, so it's positive, okay? I'm going to assume that my V naught, my V final in the y is probably going to be negative. It's probably going to be going down by that point, but let's just see what happens. Now, my g, I'm going to just use negative 10, just to make it easier on myself, okay? Oh, wait. Sorry. I screwed this up already, didn't I? My V naught is 12, sorry. So my delta dy is 12 times about 2, because 2.05 would be harder to deal with if I'm trying to get this out quick, plus negative 10 times 2 squared over 2. All right, so that's 12 times 2, so that's about 24. This one, it's going to be about like negative 10 times 2, which is negative 20. So what's that going to give me? Negative 4, right? Positive 4, sorry. Positive 4, yeah. So this is 24 minus 20. So it's going to be positive 4 meters. Okay? So the fence is 2.5 meters high. So where is this ball going to go? Is it going to hit the fence or go over the fence? Over the fence.
You redo that.
Yeah. So my t is 2 seconds. My v naught y, sorry, I need to show you how I did that. 20 times 0.6, which is 12 meters per second. There we go. That make more sense? More seconds. Okay, so then v naught y times t, so that's 12 times t is about 2 instead of 2. I mean, if I want exact numbers, I guess I can do that, but it's not going to matter because it's such a small number in relation to 2. And then g, I'm going to call it about negative 10, and 2 squared is 4. Well, 4 over 2 is just 2, so it's like negative 10 times 2, which is negative 20. So this is like 24 minus 20, which gives me 4 meters. Okay? So I'm trying to do it kind of quickly with numbers that are easy to whip out in your head. Okay. So then it says, will the ball hit the fence? No. Will not hit the fence. It will sail about, what's 4 minus 2.5? 1.5. Sail about 1.5 meters over the fence. So that's technically the answer. Yay. Sorry, running out of room because I screwed up a little. That's the answer. Will the ball hit the fence? No, will not hit the fence. How far below the fence will it hit? 1.5 meters over the fence. Okay? So, on the axes below, sketch the horizontal and vertical components of velocity of the ball as functions of time until the ball reaches the plane of the fence. What time does the ball reach the plane of the fence? 2 seconds. So should my graph be drawn beyond 2 seconds? No. And that is a big deal. Do you see how tricky that is? Because most people would go, oh, well, my horizontal component of velocity, well, that, I forgot what it was already. What was it? 16? That was 16. So I'm just going to draw a line at 16. No, you're not. You are going to draw a line at 16, but you are going to draw a line at 16 and 2. So you're going to stop your line, you're going to start your line here, you're going to stop your line there. That's all you're going to do. You may not draw it any further than the 2, because it literally says until the ball reaches the plane of the fence, which is at 2 seconds. Okay? Now, the vertical component of velocity. What is the slope of the line for the vertical component of velocity for anything that is in free fall? Negative 9.81, which is really close to negative 10. So the slope of this line needs to be negative 10. So I know that its initial velocity is 12 meters per second. So I know it's going to start at at the y, dear sweet baby in a manger. On the x is 0, it's going to start at positive 12, so it's going to start about here. So how many meters is it going to fall per second? 10. So what is 12 minus 10? 2. So at 1 second, it's going to be at about 2. How many more meters is it going to fall in the next second? 10. So then what is 2 minus 10? -8. So on the 2, it should be at about -8. And you're going to draw a straight line passing through those points, and that slope will, my bad, and that slope will be about 10, okay? I said it, but I want you to write it in your notes, that your slope is about -10 on the V versus T graph for anything in free fall. So I want you to write that in your notes. And again, why did we stop it at 2 seconds? It only takes 2 seconds to get to the fence. Okay, questions?
It's only for the vertical?
Yeah, because this is asking for the vertical component of velocity. So yeah, this -10, this slope, -10, is only for the vertical component of velocity. Because the horizontal component is constant. So it's always going to be a flat line for the vertical component, for the V versus T, I should say, for the horizontal component. Lots of V's in there, huh? All right. So, okay. So you have a little FET lab. And so you picked it up from by the door. I think I have enough computers for you guys to like work in pairs. It's kind of easy. I'm going to kind of get you started and show you what to do for it. Ooh, let me go grab me one. I feel like there's a lot of boys in my... Yeah, there are a lot of boys. There's a lot of boys in most of my classes. It's physics. It's AP physics. All right. Well, let me put it to you this way, dear. When I was in college, in my mechanics physics class, on the first day, I was one of 7 girls. After the first test,